Alright, today I have saved the best for last. We'll be talking about the binomial theorem. For many of you, this is going to be brand spanking new, and you're going to see just what it's like to learn something new and not be overwhelmed, I think. Anyways. Alright, so the binomial theorem. An expression of the form a plus b is called a binomial. Although in principle it's easy to raise a plus b to any power, raising it to a very high power would be tedious. Right? In this section we find a formula that gives the expansion of a plus b raised to the nth power for any natural number n, and then proves it using mathematical induction. Okay, so let's unpack that last sentence real quick. All right, it reads in this. Okay, let's try that again. It reads in this section we'll find a formula that gives the expansion of a plus b to the nth power. Okay, so why do we need an expansion of that? Right. Well, as mentioned. Alright, so my pen is still doing that thing. Alright, so a plus b let's make the n be squared, right? Well, we have a formula for that, right? Well, we also happen to have a formula for a plus b cubed, right? Man, I don't know what's wrong with this pen. Right, so we have formulas for those. Pretty simple. Alright, but what about a plus b to the 23rd power? Okay, it says it would be very tedious let's say same power, raising it to a very high power would be tedious. It would indeed be very tedious because I would have to write a plus b out 23 times and then FOIL it, what I guess 11 times on top of that one extra, and then I'd have to multiply those together. It wouldn't be a lot of fun, right? It would be tedious as mentioned. Right. So that's what the binomial theorem does. Okay, and then that last sentence it says, and then we prove it using mathematical induction. We won't be doing that in this particular course, but I mean, obviously you have the textbook there with you. But mathematics, as I've mentioned, at the end of the day, you just basically write sentences, right? And of course, in this particular textbook, it proves the binomial theorem through a method called mathematical induction. Right. So next up, we're not going to snip this because it's a little long. I don't feel like putting this on a couple of different pages. But anyways, let's start off. So expanding a plus b raised to the nth power. To find a pattern in the expansion a plus b to the nth power, we first look at some special cases. Okay. So what we're going to do is we're going to pretend like we are, I guess it was Pascal that came up with this. We're just going to try and find a pattern, okay? So a plus b to the first power, that's easy. It's just a plus b, right? All right, well, a plus b squared, okay, well, that's pretty easy. A squared plus 2ab plus b, a plus b cubed, and of course we see what's going on, right? Can you see a pattern? Okay, well, first of all, I mean, I can obviously spot a pretty simple pattern. It looks like whatever it's raised to, looks like whatever the binomial is raised to, seems to be the power of the first and last term. Okay, so there's one, and then of course, that was sorry, words. That was the first one there. Okay, and then of course we can see that the other patterns involved are that the exponents of a decrease by 1 from term to term, while the exponents of b increase by 1. Of course we can see that if we look. All right, and then the sum of the exponents of a and b in each term is n, right? So n being the again the power raising the binomial to, in each one of these terms, we do indeed see that 4 plus 1 is 5, right? 3 plus 2 is 5, 2 plus 3 is 5, and so on. Right? So patterns do arise here. We're going to look at these patterns and figure out how to do this binomial theorem. Okay, and as I mentioned, it's a lot easier than you think. So let's continue. Oh, excuse me, hiccups. Let's continue. My mouse. There we go. And I believe. Okay, so just basically explain what I just said. Okay, and then we get into Pascal's triangle. This isn't a lecture about Pascal's triangle, but again, I mean, the textbook is there for you if you're curious. Alrighty. Honestly, it looks like we might have. All right, let's go back and check it out. Okay, it looks like it's needed. Sorry. All right, so starting right here, we talked about how the A's do indeed increase, the B's do indeed decrease, and of course the powers, when you combine them together, do equal n, whatever we are raising that binomial to. Right. So let's start here. With these observations, we can write the form of the expansion of a plus b raised to the nth power for any natural number n. For example, writing a question mark for the missing coefficients we have. Okay. All right. So what we're getting at here is looking at the first 5 here. It actually, in hindsight, might have been better if I did snip this. All right. But anyways, looking at those first 5 that we see. We're able to see the pattern pretty clearly, for the exponents, right? Pretty clearly, that it looks like the again, the nth power, whatever power n we are raising to, is what the first and last term are raised to, and then we decrease that power on the first variable, and then we increase it on the second, right? So, for instance, we'll start here at the 5. So a to the 5, then a to the 4, then a to the 3, a to the 2. A to the first, and then a doesn't exist anymore. And then we see no b, and then b to the first, b to the second, b to the third, b to the fourth, and then of course b to the fifth. Okay, and then we do see that when we add them together, they do indeed equal to n. What we don't see is how we are getting these numbers: 5, 10, 10, 5, 4, 6, 4. We're not seeing how we're getting that, okay? And that's where Pascal's triangle comes into play. And I'm glad I didn't skip over that, because that actually is important. I just forgot how important it was. I'm sorry. Okay, so that's what these question marks are for. Those question marks are for, figuring out what is the number that you need, what is the leading coefficient of each iteration there. Right. So to complete the expansion, we need to determine these coefficients. To find a pattern, let's write the coefficients in the expansion of a plus b raised to the nth power. For the first few values of n in the triangular array as shown in the following array, which is the Pascal's triangle. Okay. So the way the Pascal's triangle works is you start at the top. So, let's see. Maybe they can explain it a tad better. Okay. Okay, they don't explain it a tad better, so I'm gonna try my hardest to explain this. Okay, so Pascal's triangle works like this. And should I snip? No, let's do this. Okay, so you start here at the top. That's pretty easy, right? And then your branches down. All right, as you branch down, you basically you're adding up all the pieces of the triangle. Should I say vertices? You add up. Oh my goodness. There's got to be an explanation. I can say it. I can do it, but I want to be a little bit more precise than the words that are about to flow out of my brain right now. Okay, here we go. I don't think we have a shot here. All right, here we go. So you start at the tippy top. Okay, 1. Right, and then the way you get this particular 1, right, you just go down and then down, so you have the 1, right? So what we're going to do here is, it's because only one vertice is attached to that particular part of the triangle, right? Now let's go to the third row before I can really explain what I'm talking about here. Okay, talking about this third row. All right, well, this particular one here is only attached to this 1. Okay, so 1 is simply 1, and we notice that it's going to be 1 all the way down. Okay, on both sides. Right. Now, what about the 2 though? Okay, well, this 2 right here. Notice how. Let's go back to the row. Notice how it is touched by this 1 and this 1, and that 1 plus 1 is equal to 2. Okay, and then let's go down to the fourth row. we see, again, the two outside ones are 1 because that's the only thing that adds up, right? 1 plus any 0 is just 1. So all the outsides are just 1. All right. Well, this 3 is a 3 because, well, it's got this 2 running to it and this 1 running to it. So that's 3. Same thing with this 3. And I've got lines everywhere. All right, and let's just go ahead straight back down here to the harder, longer one, right? And we see again the two outsides are 1, right? Well, hopefully you see where this 5 comes from. This 5 comes from 4 plus 1. Okay, this 10 comes from the 4 again plus 6. This 10 comes from the 6 again plus 4, and then so on. Okay, and that's how the triangle is created. And of course, you can go down infinitely. Now I don't know why you would. Excuse me, I don't know why you would, but you can. Right? Hopefully that explained it. I'm sure it's there's a more succinct way to explain a Pascal's triangle, but that's there you go. It's the cornbread language. All right, so let's see. I mean, I guess that kind of says it, the key property of Pascal's triangle, but I don't think you could create a Pascal's triangle just from that. It says every entry other than 1 is the sum of the two entries diagonally above it, which we did show. Okay, and it reads, from this property it is easy to find any row of Pascal's triangle from the row above it. For instance, we find the 6th and 7th rows starting with the 5th row. So we start with the 5th row, and then we just created the 6th and 7th row. And then just doing their simple arithmetic, right? For instance, we get this 21 because it is a 6 plus 15, right? And of course the arrows do help out a lot better in this one than it did in the top one. Okay. And to see why this property holds, let's consider the following expansion. And notice how it has a plus b to the 5th power, and then it is indeed using those numbers 1, 5, 10, 10, 5, 1, right? Which are the coefficients that we saw in the Pascal's triangle. Now I will admit this is not. I mean, I totally forgot about the Pascal's triangle, obviously, because no, I just did. It gets easier than this, I promise. I know it seems kind of like a lie right now, but just wait. Right? So let's go ahead and jump straight into example 1, and this is just going to be, well, it's already given to us actually. Yeah, so it's already given to us. We see that the expansion up here is for the 7th row of the triangle 1, 7, 21, 35, 35, 21, 7, 1. Okay, so a plus b to the 7th power. Oh, someone. A plus b to the 7th power is just going to be in that form, and we do indeed see this down here. Excuse me. A plus b to the 7th power is indeed does indeed have those coefficients 1, 7, 21, 35, 35, 21, 7. Okay. So example 2, same way. All right, and again, this is Pascal's triangle. Not the worst thing, not the easiest thing though, right? This is so much easier, and this is what I remembered when I said, "Hey guys, today is going to be a simple day." So let's jump right on this current page. Alrighty, so that should, let's go ahead and put 3. Alright, so the binomial coefficients. Although Pascal's triangle is useful in finding binomial expansion for reasonably small values of n, it isn't practical for finding a plus b raised to the nth power for large values of n, right? So Sorry. The reason is that the method we use for finding the successive rows of Pascal's triangle is recursive. Thus, to find the 100th row of the triangle, we must first find the preceding 99 rows. And that sounds like a job, right? So we need to examine the patterns and the coefficients more carefully to develop a formula that allows us to calculate directly any coefficient in the binomial expansion. Such a formula exists, and the rest of this section is devoted to finding and proving it. However, to state this formula, we need some notation. The product of the first n natural numbers is denoted by n, and then it's an exclamation point, but it's read n factorial. Okay, so I'm sure you might have seen this before, right? It's not the n yelling at you. It's just basically it's n factorial, meaning if we have 10 factorial, that's just going to be 10 times 9 times 8 times 7 all the way down. Okay, so that is the factorial. And of course we see that this here. Okay, so they go up, I go down, whatever. We also define 0 factorial as 1. Okay. Alright, so now the binomial coefficient. Let n and r be non-negative integers with r less than or equal to n. The binomial coefficient is denoted by n and then over r, right? But it's not a division symbol. And it's defined by, right, this is just notation. It's not a division symbol. It's strictly notation, and it's notation that you have to take seriously. And you might accidentally at some point, just because you're used to it, right? You might accidentally put a little you might do this, right? It is not the same. I'm only saying this because I've seen people do this, yet still do the arithmetic correctly, right? But get in a habit of, not putting that division symbol in between there, right? But anyways, it is n over r is just basically going to be n factorial divided by r factorial times n minus r factorial. I hesitate to say that's it, but that is it. All right, so let's look at an example. All right, so example A, it's 9. I know there's a word for it. What's the word I'm trying to think of? Binomial coefficient. I don't know. I forget. Anyways, so if we just follow along with the formula that on the preceding page, right? We have basically the top number factorial, and then we have the bottom number factorial times the top number minus the bottom number. Okay, so this ends up being 9 factorial divided by 4 factorial times 5 factorial, right? Because 9 minus 4 is 5, right? And then these numbers get pretty janky pretty fast, right? But there is a thing that there's some manipulation you can do, and we see the manipulation here is if we did the 9 factorial in the numerator, then obviously that's 1 to 9, 1 times 9, right? Well, in the denominator we see 1 to 4 and then 1 to 5. So what we could do, really, right? Because this is just basically simple algebra, right? We can cancel out 1, 2, 3, 4, 5. 1 times 2 times 3 times 4 times 5, because we see that in both the numerator and denominator. So we could cancel it once. Okay, I say we cancel it once because we can't cancel it again, right? So we can cancel it once, and then it just simply becomes 6 times 7 times 8 times 9 divided by 1 times 2 times 3 times 4. Okay, and of course we get the number 126, and then we can see that for both examples B and C. Okay, canceling out like terms, it's something that we've done for years now, and we're just doing it again, just on a different level, right? Many of you probably have a calculator that has a factorial symbol, and of course you're probably just going to use it that way. But I do encourage you to get into a habit of canceling these factors, because whenever you get to calculus and we start getting into sequences and series, canceling out factors will come in handy tremendously. Alright, so I think maybe we should snip. Yeah, let's go back and change that up. I want to snip the little note beneath it. And then we get to the binomial theorem. And let's go ahead and flip this. Alrighty, so the key properties of the binomial coefficients. For any non-negative integers r and k with r less than or equal to k, we have the crazy formula you see there. Notice that the two terms on the left-hand side of this equation are adjacent entries of the kth row of Pascal's triangle, and the term on the right-hand side is the entry diagonally below them in the k plus first row. Thus, the equation is a restatement of the key properties of Pascal's triangle. Okay. Now, the big reveal is the binomial theorem. All right. Now, the binomial theorem. If you can unpack this right here, then let's see. I'm not going to say pretty much everything that we did is. I'm not even going to say. Okay, so if you can unpack this binomial theorem, then these problems are going to be super duper easy. And for the record, I don't believe. Well, no, I'm not going to say that. You just have to. You have to know where each individual number and point goes, right? So let's go ahead and unpack it. We'll try to unpack it here, okay? So looking at the first term. All right, the first term is just simply n over 0, right? Well, what is n? Well, n is your exponent here, okay? So it just becomes n factorial over 0 factorial, okay? And then the exponent is going to be a to the nth power. So whatever, so if this is to the 88th power, right? We're going to have 88 factorial, which is, whew, that sounds like a job. Divided by, we said 1, right? In fact, we defined n factorial, I'm sorry, we defined 0 factorial to be 1. So it would just be the n factorial multiplied by a to the 88th power. Okay, well, that's the first term, right? And again, it's a lot easier than doing the triangle, okay? And then we have plus n over 1, so same procedure. And then the exponent, right? The exponent part is actually the easiest. That was part of the pattern that we were able to see, right? The a power goes down. So if it's 88th power, then the second term is going to be 87th, all right? But then the b starts going up, so we have b to the first. And then we see here, the n goes down 2, so it goes down to 86, but then we have b squared, right? But then our coefficient there becomes that particular, that number in factorial, okay, divided by, well, I'm sorry, not divided by, it's just over 2, okay? 2 being 88 minus 2. So we get to here. Example 4, use the binomial theorem to expand x plus y raised to the 4th power. So, and then This definitely is something that I could just sit there and just chug out, but I feel like it's a lot easier, especially with my handwriting and this pen not working, to not do that, right? So the solution, by the binomial theorem, we see that x plus y to the fourth power, we see that we end up having 4 over 0, and then 4 over 0, as we see, is indeed just 1, right? And then 4 over 1 is 4, 4 over 2 is 6, 4 over 3 is 4, and 4 over 4 is 1. Right? And of course that becomes the coefficient that we see. 4 over 1 is 4, 4 over 2 is 6, and 4 over 3 is 4. Okay? And I know that seems very hand wavy, but if we just go back and do this, so when we have n over r, and I even said it incorrectly, I believe, earlier, we have the n factorial over the, which is r factorial, times n minus r. Okay, so that's all we have to do. We have to understand what the factorials are, and then do the arithmetic behind it. And that is what the binomial theorem is about.